Thanks for the intro. Yeah, happy to be here. I'm kind of a reasonably long time attendee of the New York meetup, and then since obviously the event happened, I think Kevin said earlier, it's hasn't really been happening quite in the same way, but at least I've been able to go around to all these other Rust meetups, which is nice. So let me share my screen. Thanks for the intro. Yeah, happy to be here. I'm kind of a reasonably long time attendee of the New York meetup, and then since obviously the event happened, I think Kevin said earlier, it's hasn't really been happening quite in the same way, but at least I've been able to go around to all these other Rust meetups, which is nice. So let me share my screen. Okay, cool. So yeah, I'm the CTO and co-founder of Oso. We've got my co-founder Graham here as well, and also Steffi from the team. And yeah, as Scott said, like the main thing we're building is this open source policy engine for authorization that you can like embed in your application. And I'll like talk about some of the different layers of that and how Rust all comes into it in a bit. So yeah, so before I was doing Oso and everything, and what came before that, I was doing a PhD in cryptography, which is really where like my experience with Rust all began. I did sort of an internship at Mozilla kind of early on as part of that. Heard Rust everywhere and kind of eventually was like, all right, I should probably check this thing out, and sort of fell in love with it. And kind of luckily as a PhD, no one really is ever going to use the work you produce. So it didn't matter if I was like, cutting my teeth on Rust. And kind of, I kind of fell in love with it. Cryptography is obviously very, a lot of that is around security. Rust offers lots of great security guarantees, but also, the performance, the efficiency, the abstractions, everything that kind of we all know and love about it. And so now I'm CTO at Oso, been on a company and kind of get to have that ability to convince Graham to let us use Rust as our as our sort of main language. So here's the Oso team and extended family from pre-COVID times when we could still do this. And there's Steffi, who wasn't with us when hadn't joined us yet at the time, but I feel bad every time I miss off her photo on this. So there you go, Steffi. So basically, okay, so my goals for what I want to do today, I want to show off the Oso product and the kind of language piece of this, which is called Polar, mostly because I think it's really, really cool and heavily uses Rust. But I want this to be accessible to kind of everyone here. Like, it sounds like there's a really nice mix of experience with Rust here. Some people have been kind of some people are using it, some people are new to it, made it through the book. Like, that's awesome. And some of the experiences of what we were doing, it led us into some of the kind of murkier corners of Rust that you maybe don't always get a chance to play around with. And I found it interesting and challenging and fun. And so I thought I'd share some of those experiences, especially because some of the things I hit really, like when I had to dig in to understand them, I kind of started seeing that same pattern or error in a lot of different places. So I thought it was kind of fun. So with those goals in mind, if I'm going through something and I just like blew through a piece of whatever Rust code thing, terminology, whatever it is, please do just like comment in the chat. I don't know, unmute yourself and just ask me a question. Like, I'll happily pause and explain something. So, okay. So what I'm going to talk about will be, I'll give a little overview of Oso just to kind of ground where this is all coming from and the context of this. But I won't spend too much time on the kind of what the product does in the authorization side of things. This will be more about some of the language aspects. So I'll talk about the Polar language, which is the core of the open source authorization library, and kind of how we built some of that stuff. And then really this third bullet point is the main thing. I'm going to kind of deep dive into how we had to build that Oso Rust crate. And, first you'll see like why we had to build it in the way we did. And then I kind of walk you through how that actually went down. Okay, so again, Oso is a policy engine for authorization. So you write policies, you express your authorization logic in the Polar language. This is what you see at the top. So this would be your Oso policy, where you're going to express who can do what in your application, and specifically the logic of which. So imagine you're building a B2B SaaS app for managing expenses, and you want to say, a user can only read an expense if they were the one who submitted the expense, right? So that's what this rule up here is capturing. And there's a bunch of things going on here. This maybe looks, there's some types going on here. Maybe looks somewhat similar to Rust. It's not this, this allow things kind of like a function. So, it's this, but this is the Polar language, right? And so these are authorization rules. There's semantics for things like types, which I'll go into. There's semantics for things like accessing attributes. And the really cool, like the core piece of this, and like the sort of entire point of this talk, is that you express logic in this Polar language, but it's written over your application objects, your application types. So on like the Rust side of things, for example, in your code, you would just call like the very simple also create API just to say, you ask the question, is allowed. Is a user allowed to read an expense? Returns a result, returns a bool. And you're passing in these user object. You're passing in a user class. You're passing in a certain user struct or an expense struct. And the policy up here above will be checking, is this user of the user type? It's looking up these attributes and stuff like that on those Rust objects. And so the whole point of why this exists is so that you can write your authorization logic separately from your business logic, right? So typically these like if-else statements will be multiple nested things, like, oh, if the user is in this role, or if they're an admin, or if this particular thing is a private piece of data that no one should see. That often gets like very messy and wrapped up and complex. So the idea is you pull all that out, you get to cleanly write it in this kind of powerful logic-based programming language, and your application just gets to call like a simple API. So the language itself, Polar, is all built in Rust. That's like the core of the language. And we chose that very intentionally because we wanted it to be embedded in multiple languages. And Rust has a pretty good story for exposing things like a C API, and also a really good WASM story. And so that's the core bit you're seeing here at the bottom. Then what we take that compiled library, and we are embedding it in like different language libraries and packaging those all up, right? So we have Node supported through the Polar WASM library, Python, Ruby, and Java supported through like the C library, that like dynamic library, and then like the Rust library itself is just building on top of the core library. It doesn't need the interface, hopefully for somewhat obvious reasons. So yeah, but the main point of today's talk will be around the Rust side of this, the also create, like how do we build this one, which in theory, going back to this slide, should maybe have been the simplest one, right? Like there's no API layer. These are all doing some like passing back and forth JSON strings convert stuff and having to deal with that kind of thing. In theory, it should be the simplest one, but because of the kinds of things we're trying to do, checking these types, dynamically accessing attributes, it was actually pretty tough, pretty challenging. As we were going, we had a lot of fun. So we kind of we took some notes along the way, and I've been turning them into sort of a series of blog posts, kind of chronicling the various things we hit upon. And that's like largely what this talk is based on, is some of those stuff we kind of jotted down along the way. Okay, so I'm going to jump back into, I'm going to show some codes, again, to kind of set the context of what OSO is doing and the sort of interface we have. So, okay, if people are familiar with Python, they've probably seen Jupyter notebooks before. There is actually this project called EV6R, it's a Google thing. They actually provided Jupyter kernel for Rust, and they have like a Rust REPL and things like that, which is kind of nice, which I'm using to sort of make this whole thing a little bit more interactive. Okay, so here's what it looks like. I install the OSO crate up here, and I can create instances of the OSO object. I can then load in my policy as just like as a simple string. All right, so I'll load that. And here this rule is saying I have a rule which is called element and list, takes in a single input element, LM, basically just a variable, and it's saying this whole thing is true if LM is in this list 1, the string ABC, or a dictionary mapping B to 3. So I load that in. And then I can now query this, right? So I have OSO query rule, I'm querying that element and list rule. I'm passing in, these are basically variadic arguments, so I need to turn it into a tuple. So I'm passing in just a 1. So I'm kind of querying, is 1, element and list with 1, is this true or not? And right, so it's going to check, is 1 in this list? You see there's like, some is saying, yes, there is some result, and okay is like, well, it's just the result is an okay result, and there's no like additional information to provide. Similarly, though, I can check if 2 is in the list, or 2 is an element in the list, and I get back none, there was no result. So immediately to point out, like, so this is a logic-based programming language. So what you're actually doing is like, you're querying it with like a, in this case, the rule you're trying to match and like an input, it's not just returning necessarily like yes, no answers, potentially returning like all of the results which are true, or there are no true results, that kind of thing. So if I go down here and I have another query rule, but this time I'm passing in a polar value, my real favorite enum, my polar value enum, and a variable type. And this time instead, I'm just gonna like keep on popping off results from what I get back from the query result. And okay, cool. So you see I get some integer 1, I get some string ABC, and some map B to integer 3, right? So these are now, I've now queried my polar policy, this element and list rule, and I'm actually getting back the results. And because, this is, we're happy to have heterogeneous lists, we can have integers and strings in this list, we're getting these kind of wrapped inside this polar value enum, so we can actually support back getting any of these. And there are various different APIs. If you already know the expected type, you can just like ask for the right type back directly and convert it that way. So this is what it looks like in Rust. And as I said before, we kind of intentionally wanted this to work across multiple languages. So if I hop over to my Python Jupyter Notebook kernel, you can see me doing the exact same kind of thing. So from OSO, I'm importing OSO. I'm gonna clear on my output to avoid spoilers. Doing the exact same thing, right? I'm defining my rules as a string. I can, my syntax is a little bit different here, but I'm querying rule again for element at list. Python has variadic arguments. I don't need a tuple. And the bindings is the same as that like inner type I was getting before, this thing, right? So this is the bindings, and the thing I'm kind of calling get on here is the same kind of object. So yeah, in Python's case, this generator is empty, so it's done with generators instead of kind of like iterators. Python's not as statically typed, so it's pretty happy for me to get back various different results from this query. It doesn't need to all be the same type. It can do anything, and so on. And okay, and so like this is like a full-fledged language, which means there's kind of nice things involved. Like you can, if you have an instance of an OSO, this the policy engine, you can drop into a REPL for it, and I can start writing little REPL queries and doing things like that. So I can say. And it does like logic-based operations. A lot of it is very, very heavily pattern matching. If you enjoy writing like match statements in Rust, I think you'll really appreciate this like ability to do this kind of syntax, right? So matching two lists and it's able to assign the values. I can do that, and I can have like some of them specified and get back just like the suitable missing values. I can kind of go crazy and mix and match them and so on, so on. Let's say this is maybe whatever, 2, 3. Cool. So that's sort of the high level of OSO and kind of Polar and what's going on. And hopefully that gives you an idea of the kind of interface we're looking for and the sort of basic interaction, right? You have this back and forth between passing things in from the Rust side, right? I'm querying, I'm passing in a Rust integer. It's getting evaluated inside this language, this policy engine, which is able to work across any of these languages, right? It's the same core language, the Polar language written in Rust, that's working with Rust, with Python in kind of the same way. So it's like this kind of translation layer going on, and so on. Okay. So the whole thing here is around like runtime reflection in Rust, because as I said, like when we first built these, the very first version we did of this was in Python, and Python is very, very nice and dynamic. It's incredibly easy to do. If I think I'll need to. I don't know how to exit the REPL from here because I can't control D it. Can I like manually control D? No. Let me just restart this kernel. So for example, right, if I have, this, like at runtime, I can ask, what's the type of 1 or something like that, and it's an integer. I can get the attr, and I can like dynamically get attributes or something from integers, and it's like a method bound, right? Like Python, very, very, very heavily dynamic. You can do all kinds of crazy metaprogramming at runtime. And you'll have a lot of fun, but Rust is not like that. So we needed some sort of system for runtime reflection Rust so we could do this, right? Like when the when the language is evaluating some of these things, and we'll kind of go a bit further, like I haven't shown many of them here, but in the initial examples I gave, right, I was trying to look up attributes on a struct. Like how do we enable that? And basically there's like three like main areas we identified that we needed for this like runtime reflection. It was like classes, attributes, and methods. So what I mean by dynamic classes, so if you write a rule like this, check foo, where foo must be a foo, and you have some conditions. So this typing here, it sort of looks like Rust, but the difference is you can have multiple rules. The kind of semantics for multiple rules is that it's sort of an or, like any of them might apply. Like I might have 3 or 4 different check foos with different conditions in them. And so the type parameter here is what's known as like a specializer. It's kind of telling us like, can I apply this rule or not? Not like, so you might have 2 or 3 different rules with different type checks, and they should only apply to the specific run. And so basically what we need the Polar language to be able to do is ask our host language, ask Rust, ask Python, is this thing that I have in my hand, is it actually a foo? So the kind of core piece for dynamic classes in Rust is this trait called the any trait, which I think I'm getting a bit of a reputation for overusing the any trait, but it's kind of a fun one. And it's kind of nice, right? So right up here in the docs, it says a trait to emulate dynamic typing. It's like, okay, cool. This is pretty much exactly what we want. So let's see how it works. Oh yeah, I didn't go through this as the application classes. Oh yeah, I'll quickly go through this. Actually, I forgot to go through this earlier. So here are my rules, like checking if a thing is a cath or not. I can, so here's what I was saying, like I have a rule which expects a cat. If I pass in a 1, it's not like a failure. It's not a type error or something like that. Hey, I expected a cat, you give me a 1. It's just saying that this rule is not going to match. Like, okay, I'm not going to try and apply this rule of this being a cat or not. Whereas if I do pass in legitimate cat objects, then there we go. Everything's fine because I didn't have any conditions here. So this is just like, this is basically like if true. And so there's a little bit going on here. I derived a Polar class. I registered the class. That's how I'm able to use it. And we'll kind of see some of that in a bit. Okay, sorry, but coming back to the any type. So I have a simple string here, the hello world string. Technically a static string, which I'm converting to an own string. What I can do is I can box it and sort of cast it to the any trait, right? So if you have like traits and you want to treat them as objects and pass them around, because they're like not sized by themselves, right? Traits represent behavior. They don't have a concrete size. They're not actually like a concrete type that you can pass around, throw around, because Rust won't know, like, this could be some giant struct with a million fields, or it could be like a single integer. All I know is that it implements some behavior. So basically putting it inside a box is, you're effectively putting it like behind a pointer. So it's like, I don't know what it is, but it has the behavior I'm expecting. All right, so when I do this, right, I'm sort of erasing all my information about the fact that this S is actually a string. So if I try and print it, for example, it's not gonna let me. It's like saying dyn any, like this is all it knows about it. It just knows that it implements this trait any, and it can't implement, format to the default formatter. You can do the same kind of thing for like other traits. So instead, imagine I was saying, well, I'm going to pass around instances of display. Like, I don't know, it could be a string, it could be something else, but all I know is it's displayable. Then in this case, I can actually still print it because Rust just knows that it has the right behavior. It doesn't need to know it's a string to know how to print it. But if I try to do like debug printing instead, that's not going to work because it's like, I only know it can do display. I can't quite get to the full debug implementation yet. I'd have to change this to debug and so on. Okay. But not all hope is lost, right? So we've like erased the concrete type. We've sort of forgotten what this string actually is. All hope is not lost because we can still get back the concrete type. We just need to do this dynamic check at runtime. And so that's what's happening here with this downcast method, which is it's very related to this it's very similar to this downcast ref that you have on on any, but in this case, it's actually implemented on box itself. But it's the same kind of idea. And this is basically going to return a result. So I'm just going to, panic if I fail, if I got the wrong type. But it's going to get back basically a result, maybe with the string. And if it fails, it'll just be the original type. The thing I'd get back would still be boxed, which is a bit of a pain. So I'm just going to deref it so I can get a proper string back. And right, now that I get a string back, I can call string methods on it. I can print it again. Everything is fine. So it's gone through this like full cycle of it was a string, then I forgot completely what it was, and it was effectively like a JavaScript object or just a Python instance or whatever. It's pretty flexible, but I can get the type back and do things with it if I need to. So that's kind of piece one. And this is actually a very, very simple but very, very powerful thing, because now I can actually pass like arbitrary types around and kind of forget about them. And so the kind of implementation that we ended up with made this sort of distinction between a class and an instance, where an instance would be the thing we actually pass around, this like boxed dyn any, and the class would be something that remembered the type. So so in this case where I got back the string and called methods on it, this is okay if I know that I'm getting back a string, but if but I can only write this method concretely because I know I'm getting back a string, and we'll see in a bit that that's not quite sufficient. We're going to need to like remember more about the class, and we'll see that in a sec. So okay, so dynamic attributes is the other piece we need. So again, we have our rule. We checked that it's a foo. It's not quite that useful yet that we just can check the type. We probably want to be able to do something with the struct or with the attributes itself. So what if I want to read a value off of that Rust struct, comparing, so check it's less than 2. Sounds like it should be okay to do, but it's actually super, super hard. And kind of the sort of intuitive understanding for why this is because Rust sort of reserves the right to do whatever the hell it wants with your struct. It's like you give me a struct, and if you haven't referenced the attributes somewhere, you haven't made them pub, like I'm gonna rearrange them super efficiently for you, which incidentally is a very, very nice feature of the language. But yeah, if you didn't quite lay out your struct in the most efficient way, I'll reorder them so I can fit a little boolean alongside the integer, and then it has the right padding and all that kind of stuff. You can sort of opt out of this if you've seen the sort of hash square brackets repr C that's saying, I want to opt out of the Rust version of this, like just do what C would have done, put them in the right order, and then you can kind of do similar things like pointer arithmetic to find where the field would be if you really want to do that. But we kind of wanted to avoid forcing that on our users. We looked into a ton of different approaches. It's like it felt like a very tangible thing we could do. It's like there are traits like index, where it's kind of like indexing. It's can we sort of kind of think of a struct as a dictionary and like read a string? It doesn't quite work because that expects all the types to be homogeneous, and then you don't have that with a struct. Serde is the kind of thing I normally reach for if I want some of this kind of like data conversion style things, but we felt like it would be kind of it just felt wrong to just kind of mix those two concerns. One is around data serialization, and the other one is around like axic attributes and reading attributes of a struct, and staying inside the application really. And so there's a bunch of different approaches. We kind of laid out some of the pros and cons of them in the blog, but ultimately landed on just doing an attribute getter. It's a reasonably simple pattern that works really nicely. And kind of the general idea is that you have this like hash map from the string, the name of the attribute, to an attribute getter. The attribute getter is more dynamic trait goodness, but in this case, the dynamic trait is the function trait. So saying an attribute getter is really something that can take in a reference to my a reference to my instance, and can return the value. It's kind of putting it simply. So yeah, so this is what this ends up looking like. It's pretty clean. So you say, so we have this kind of system for allowing you to kind of build a pattern for defining the classes and how to access things, or you can do it through the drive macros as well. This is actually doing both simultaneously, so that's kind of unnecessary. But if I got rid of this, for example, Oh yeah, this is doing some weird things. There we go. Foo.x. That sounds good. Let's try that. So you can see what I'm doing. I'm basically providing, I'm providing OSO, or I'm providing Polar with the way to access the X value from the struct, and it's super straightforward, right? So this is a closure. Basically, if you're not familiar with the syntax, it's actually like a little inline function. It takes in a foo and it reads the foo.x value and it returns it. This simplest getter you can kind of imagine, but basically what this is kind of doing, right, is we're in some ways allowing Rust to still do what it wants with the X value, but we're just saying, just make sure you give me a way to get that X value back. And you kind of see this in action at the bottom. So I have a rule which is checking if the X value is 1. I pass in 2 different foos. One of them works, the other one doesn't. And there's a kind of a nice property here as well, which is that there's a lot going on here which kind of isn't displayed, which is kind of just wasn't theoretically necessary, but makes for a very nice UX experience. So if I was to actually pass in a function which wasn't a getter on foo, that for some reason, I tried to pass in a closure, I got the type wrong, I typoed it or something. This attribute, that's not even gonna work. First of all, let's try that. Here we go. So this attribute getter, because it's the builder on the foo struct I have, it's expecting this to be a closure that has foo as the first input. And so I'm just getting a type, I'm using the Rust type system, even though we're actually going to go through this whole any system and kind of forget what the type is. It's just kind of like a nice, you have this like nice ability to like really make sure the types match. Okay, so the last one I want to talk about is dynamic methods. So yeah, for example, you have your foo again, and you want to call some method like getX on it, which to start with, we basically take more or less the same approach. Like the attribute getter pattern actually worked quite nicely. Passing in a closure, telling it what the name was, that was actually kind of a reasonable thing to go with. The complication is that you need the function to also be able to take in arguments potentially, and we don't require it to be like have singularity of the inputs. So we kind of expect like a vector of values. So the first attempt at this looks something like this. We were like, all right, cool. We'll have a function tray. It'll take in a vector of arguments. We'll do the conversion like in this like blank in the implementation for the trait, and then we will like call it. Like everything sort of seemed pretty reasonable. And we'll then we can like pass around this trait as similar to like the attribute getter. But this didn't work, and this is like one of the things I referenced at the beginning is like an error that I'd seen a ton and never really quite grokked until I had this experience with it. So I thought it'd be interesting to go through it. So here I have this similar kind of implementation. So I'm trying to implement this function trait for, so just walk through the syntax here. So I have a trait. It has a single method invoke. So I'm invoking the method on a vector of these polar values and expects a result type. So I want to say, okay, I'm going to implement this function trait for any function which goes from some value a to r, where a I can convert from polar and r I can convert back to polar, right? So this, a can be an integer and r can be an integer or a string or something like that, right? So I'm getting this error here saying the type parameter a is not constrained by the input type trait, self type, or predicates, which always gives me pause because I'm sort of like, well, it's right here, right? Where a, a is up here, a is here. I feel like I'm doing pretty well to specify it. And I think it's particularly hard to see what's going on here with the function trait, because like I look at this and I think this feels like a reasonably concrete like trait type. It goes from a single input to a result, but technically this could match like multiple different functions. Like this isn't the concrete type. This is the same for anything which implements the trait function from A to R. And in the future, Rust might give you the ability to implement this trait yourself, which means you could define your own struct and implement fn from integer to string, or from string to other string, whatever you want. So it can't really know that like which A you're referring to. And like I'm using it in the body to try and convert the arguments, but it's like you're implementing it for a type F, which implements this trait, but it might implement multiple of them. You can actually avoid this by instead like doing this over, for example, a concrete function pointer. So I can say if instead this was a function pointer from A to R, I got rid of this and I got rid of this. This should now work. Yeah, compiled fine. So this is different because this is saying this is a concrete function pointer now, like not just a type that implements function, but the function itself. However, this actually results in a really poor UX experience, and it's because of another sort of weird, interesting aspect of functions, which I'll kind of go through reasonably briefly. But so here I'd have just an empty, like trivial trait. I implement it for functions A and also like dynamic function points, like dynamic function traits, like my dynamic objects again. So I'm going to implement that. If I now try and take a closure like I had before and say, well, this should be a my trait now, right? Because I implemented it for functions. It's not happy with me because my trait is not implemented for closures themselves. So closures like this, they actually have their own unique but anonymous type. Like I can't reference this in any way, but it is a legitimate type, and that type is not a function pointer like fna. Which means if I actually wanted to use this, I would need to do this kind of thing down here. I can cast my closure to a function pointer, but they're not the same thing. And I think this is like an optimization thing. It's like technically this is like the direct like address for the function call as opposed to like a pointer, which you'd then have to like read the pointer and find the function address. It's like a little kind of one instruction hop. And yeah, basically similarly for real functions as well, which I think is actually kind of an interesting one as well. If you look at I was like, surely function test A must be this function thing. That looks like they kind of match identically. And if you've ever seen this and like been confused what's going on, like not implemented for function U32, that's exactly what I implemented. The trick is in these curly braces test fun bit. This is trying to hint to you that this is not a function pointer. It's an address of the function. It's like, again, this concrete, unique, anonymous type that you can't actually reference. So yeah, just kind of a few kind of interesting oddities that I found for like functions when they don't quite behave like you'd expect them to. The upshot of this, it means you need to do like a lot of these coercion things if you want it to work with these above trait definitions, which is just horrible, right? Like imagine if I had to do that for all of, here's an example of this, like how this actually looks in OSO. I can just pass in the method bar : add things and like reference it in that really like nice, concise, like Rust function syntax, instead of having to be like, oh, and this is what even is it? Fn and bar takes in a U32, the output's a U32. Like if I had to write this for every single like class method I registered, this would be such a pain. So this wasn't acceptable. If you end up with this kind of a problem, the simple trick is to, and I don't know how many iterations and attempts this took me to get here, but the trick is basically to add the thing that you are trying to like write a trait over into like some generic parameter of the trait. And because this resolves it, because I can now, I can implement method, in that case where I said I'd implemented a function for a string input and an integer input, well, that would be two different implementations of the trait. There would be one implementation where arg is a string, and there'd be one implementation where arg is an integer. These two things are now disambiguated. Everybody's happy. So I'll probably leave there. If people are interested, there are some other really nice aspects of implementing some of this library that didn't actually require too much work themselves. They kind of fell out of how we'd implemented the other pieces. So like class methods we implemented we sort of followed a kind of Pythonic way of doing this and had like we registered the class struct itself as a class, and then class methods is defined as methods on class, which take it in like a class, which is kind of nice. And you can also do like iteration result types and things like that. There's actually a lot of people out there who are building languages on top of Rust, or in the case of this like Pyoxide project, they're building Rust bindings for like a Python interpreter. But it seems like a pretty popular thing. I think there's this balance between this desire to have something meaty and powerful like Rust, but maybe that kind of escape hatch to sometimes be able to do something a bit faster. And interestingly, they all hit the same problems that I kind of walked you through today. This kind of like, how do you do functions, the function trace, and how do you deal with those? How do you deal with like types and dynamicism, all that kind of thing. Cool, so that was all I wanted to cover. If you want to learn more around the OSO stuff, then here are some links. As I mentioned, everything I've spoken about and everything we're working on right now is fully open source, and it's all available in this one repository. It's kind of nice. You can see the language core, you can see the OSO library, you can see all the other, I don't know, how we build Python packages on top of Rust, and our 200 CI jobs to build them on every different platform and things. We'll always love to have people come into the OSO community and chat with us. We've actually got a few people who are using the Rust OSO library as well, and have been like contributing back to the library and stuff like that, which is great. And yeah, happy to answer any questions. Thanks for listening.
Cool. Yeah, that was awesome. Yeah, so we'll keep recording. So just as a reminder, if you do want to ask a question, and you don't want to be possibly videoed, remember to keep your video off. I'll start first with Mitch had, I think he pinged me directly.
I see a chat, but I can't get it up.
Okay. Yeah, he pinged me directly to say, what is Polar?
So Polar is the policy language. So if I just go back to, so basically, so the OSO library, this is the thing you would add to your application, whether in Rust or Python, that kind of thing, and provides this interface to allow you to make authorization decisions. It's like the main idea of OSO is around authorization. And so it provides you an API, like it is allowed method to make authorization decisions. But what it's doing, it's evaluating your policy logic, which is written in the Polar language. So that's like the piece at the top here. The name of the language is Polar, but you're sort of interacting with the OSO library, which is embedding the Polar language inside it.
And then I guess then like that it kind of is forming the universe of things that can be a Polar value, like the sorts of structs and the data structures that make sense within the context of that language, the numerics that it supports and that sort of thing. That's where then the Polar values like are determining like their universe within inside Rust.
Yeah, exactly. Polar itself is fine if you want to dig around it. It's in the same repository I linked earlier. Yeah, nice. It's in the same repository. The language itself is kind of fun. It's so as I said, it's a logic-based language, but we've got like a kind of VM-based implementation. You can go through, you can see we're using things like the ladder parser, and we have this like virtual machine which like is iterating on these goals, and it has this very nice. So the design of it was meant so that it can be embedded in other languages, which means that while the VM is operating, it might need to ask questions like, lookup, right? So, or lookup external rather, like, I want to get this field on this instance from Python or from Rust or from Ruby or whatever it is. So it needs to be able to basically like pause the entire virtual machine, like midway through evaluating the policy, and say, hey, Python, can you get me the X field on foo? So, and that's why we have this like virtual machine approach, because basically, to pause, you have your entire stack, you have your like stack of operations, you just like leave it, return back to Python. And so there's kind of like this event loop approach where the entire execution is driven from the host language side, so from Python. So so when I call, when I'm calling is allowed, it's like, creating a new instance of that virtual machine, and it's basically like it's telling it like run until you get the next event, and the event will be like, hey, can you check what type this thing is? Hey, can you look up this attribute? You return back the answer to the question, and basically tell it to continue, and it kind of goes on and on. And what the model means is like whatever your runtime looks like. So in Node land, this is async promises. In Rust is in Python, with GC and stuff like that. It doesn't matter the runtime, because it's all been driven by that host language, and like the execution of the policy languages can be paused and continued without problems, which led to some very tough things. We do, there's like a sorting algorithm to choose which rule to execute next, and we had to implement this sort of like effectively an asynchronous sort in this VM approach, which was tricky.
I'm curious, like looking at the example you have there, like one of the things I would imagine when you're deriving polar class is that you're including that name so that when you pass in an instance of user, you've already like stringified the type user so that polar knows like, oh, this is a thing that should have all the things that I'm looking for. Do you have like name? If I have two different things called user, like two different places in my.
It won't let you.
Okay.
Yeah.
Okay. Cool.
So it will. I believe it currently defaults to like the fully parameterized like string name. Maybe not actually. No, the derived one doesn't. But you can, yeah, I mean, you can basically include the full path of the name if you want to disambiguate them by module or something like that. But yeah, so like here we have the current language implementations. So inside the OSO one. So these are the definitions I was talking about earlier. So this is the class object, which yeah, as I said, has like the string name, but also things like the type ID, which is coming off of that any trait, and allow us to do some dynamic type checking. And then yeah, carrying along things like those attribute getters and the method. So the class like carries around all the meta information of what the class can do, which is the way we get around like not actually being able to call things dynamically. And then if you go down to, for example, the instance itself is, okay, instead of boxed, it's arced because we clone it a ton. It's reference counted. But effectively, the instance, the thing you pass around is just this fully type erased object. And if you want to check if it's if it's the same instance as a class, you compare type IDs. If you want to get an attribute from it, you look up the class. Now you have the class object, you have all that lovely information about what the class should be able to do. So you can get the attribute getter and invoke it on the instance, and it knows how to do the right type conversions. And there's a bunch of the implementation of this is buried inside some of these kind of like these like shim layers. So this is the thing which takes in the closure I passed in, right? So I passed in like foo.x returns x. So that's my like base function implementation. Like any trait that does that is fine by me. We're then using the type information we have to construct a new inner closure, which is going to like shim the type conversion just in time for us. So we're going to have in our hand an instance when we call this, but it like this closure knows, it kind of effectively remembers like, oh, okay, I should downcast the any trait to an instance of t so that I can call the function on it, which is kind of the sort of nice part of this is yeah, it's like where the type's happening. So we kind of, I mean, we handled the error, but it's this error should effectively be impossible. That's why we have it as an invariant error, because we've kind of guaranteed that we are passing in a thing that can actually is of the right type and the function is the right type.
Cool. Anders asked in chat if the syntax of the Polar language is fairly stable by now.
Yeah. So basically we launched the first version of this back in August, is when we open sourced it. For the first few versions, there's a fair bit of iteration. Effectively, we were trying to get towards what we felt was like the kind of simplest and easiest to learn syntax possible, which I think ended up with something sort of looks somewhat like, oh, I have a crazier example to show. It sort of looks something like Python. You write ifs and ands, and you can compare values. This is a bit of a more out there example of using. This was based on a project there was some students that we were helping work on a project who were building a poker hand analyzer using the Polar language. So this is kind of based off of that. So this is a logic to capture like scoring a poker hand. And yeah, so it kind of has I don't know, I think it's a nice example of the syntax, right? We've got things like lists. This is me calling like a Python enum. What else do we have in here? Yeah, we've tried to keep the language pretty much as small as possible. Like other than the kind of core operators like and or comparisons, there's not really a whole lot going on because it sort of feels sufficient for, and like basic arithmetic, because that's generally the main things you need for authorization. There's a little bit, I guess the other thing going on here is this like tail args thing. So if I have a list, I can match the head and the kind of the rest of the list. I'm gonna actually demo this one quickly because it's kind of fun. So here's the Python code, just to like does some like the parsing. But what I can do, I can pass in like a hand, and it will score it for me using that polar logic. So if I run this, so there we go. We've got like this one looks like it's got a pair of 2s and then ace 4 3 and so on. As I said earlier, logic-based programming languages don't necessarily just return yes or no results. This one at the bottom is going to return all of the hands I could make with these first 4 cards. So I have this syntax here, which is like question marks is any card you want. So if I continue on this one, this is going to give me a ranked all the possible hands I could make with those first 4 cards in the ranked order. So the best I can do is get 3 aces, for example, 5 4. And maybe the next best thing I could do is do 2 pairs, aces and 4s, or aces and 5s rather. So it's kind of fun.
Cool. I wanted, so nobody, I said it in chat, but as a warning, I will keep asking questions so other people don't ask questions. Yeah, so what were, aside from like being easy to embed and like being relatively simple, what were some of the other design considerations? Like, were you looking at like, oh, this needs to run 5 billion times a second, or it's more important that it is really easy to trace and show somebody why it decided something?
That's a really good question. So performance was definitely, performance is definitely a concern. I wouldn't say we definitely haven't exhausted the performance that we can wring out of this. Most of the recent like major performance improvements we've made have been kind of on the algorithmic level. So for example, if you're checking whether an element is in a list, it'll kind of do that. It'll sort of do that as fast as you expect. Indexes rules and checks like the types up front, because that's one of the more expensive things, like stuff like that. We actually have our benchmarks on the website. So, oh yeah, this was like the last time we did some amount of simple optimizations, for example. So this is for like the base operation, is we're talking like 800 nanoseconds. For like substantially more complex rules, we're still in the maybe tens of microseconds, sort of generally in the sub-millisecond range. These are some particularly horrible ones we wrote to test like a kind of n+1 like behavior. But yeah, the general performance right now, it's for every kind of policy we've seen, it's normally in like the sub-millisecond range. There was like a whole area of work we did, which is around performance, but in a kind of a bit of a different way, which is this topic called like list filtering. So the general problem space is if you have like a web endpoint, which is an index endpoint, right? Like a list all the expenses, then the authorization decision you want to make there isn't necessarily like yes or no. And in particular, you don't want to get like your entire database back and go through and be like, this one, yes, this one, no, this one, yes. So what we've recently done is made it possible for the policy evaluation to return kind of like a set of constraints, which can get converted into like SQL operations and performed at the database layer. So that was like the next like huge step up in performance. It's like Rust by itself just fast enough. Like we mostly cared about writing the code cleanly. We use arg everywhere, so we're doing reference counting. It's like kind of pseudo GC, but it's still pretty fast. Like we haven't worried about optimizing that to the death because like Rust does such a good job of that by itself. So it's more about being able to like quickly implement those new features to like get those really huge improvements.
Cool. Audio better now?
Yeah, sounds like it.
Okay. Yeah. Yeah, I guess yeah, sorry. I don't know
You're
how
saying like
much
what are
dropped
some of
off.
the stuff we have to do to get around like the Rust type system, or like to work around some of the Rust
Yeah,
things?
right. Like you can't put arbitrary, like any unlimited number of arbitrary custom, like user-defined traits in a dynamic trait object,
Oh,
a
right,
single
right, right.
dynamic trait object, right? Like that's one that in particular was like, oh, this isn't panacea. It is a tool for specific
Yes,
use cases.
yes.
And that was one example of like a limitation. Maybe there are more interesting ones that you encountered and had to get around.
I mean, that is an interesting one. It's one that we are currently, still not around, to be honest. So if history, oh, I guess it's here. Yeah, so we haven't got around that one. So the way we like the way we make it possible to use some amount of traits on those like dynamic objects is kind of the manual approach right now. So if we go back to class, for example, you'll see things like this. We have this equality check field on the class. And this is basically our current way of being able to support equality is you need to tell it explicitly how to compute equality. Like we can't just say, let's try and use partial equality, because basically there actually is, there basically is no way of dynamically getting trait information on something without in some form registering that up front. And so on the first blog post we wrote, the runtime reflection in Rust 1, part 1, we kind of raised this I kind of raised this as an open question. Like, I'm not sure how to do this for traits, because in Python land, for example, you can use classes and subclasses as specializers, and it'll like match if it's match if the object is of the class or any of the the subtypes, things like that. So we thought it'd be really nice if you could do that with things like traits, or if you could use trait methods, but we haven't really found a way around that. It's just the way that they're set up is you just can't safely know if something has like actually implements a trait or not when like dynamically. Like once you lose that information, you can't really get it back. So like this is our current workaround for it, right? So we allow you to manually set an equality check, but you can also say with equality check, and anything that implements partial equals will just like hard code that as the sort of default way of doing things. And this is kind of one of the bigger limitations in this, is that basically if you want to be able to use a trait dynamically in Rust, like you need to do some amount of work up front to tell it that so you can use it, which is a little bit unfortunate.
Cool. Are there any other questions? I have one final question. I want other people to be able to jump in, but or continue your thoughts. Sorry if I'm cutting you off.
Well, I was going to say, I think there is maybe like one area where this could get better, and it's around there's like this open topic around like specialization, which is the ability to write like default implementations for things, but then like override them if you have like a more specific implementation. So that might mean that, I'm not sure, because for example, right now, we have like this kind of blanket implementation for anything that implements polar class, how to do two polar on it. But yeah, I'm not sure exactly how we could. Do I have it? Where do I have it actually? Oh, it might be here. Okay. So like, okay, so here's our like, this is basically the default implementation for the polar class trait. So if you just do impl polar class for foo, this is what you get by default. If I don't know, if Rust made it possible for me to have like, this is a default one, and then maybe write like a default implementation for any polar class that implements partial equals and implements clone and implements blah, and maybe I could like, macroify all combinations of the like core traits that I'd want to implement this trait for as a default implementation. That would like solve like one of our problems in a heartbeat, because then the derive macro can just basically say like import polar class and you'll be done. Otherwise, the only way we can currently like pick up if you have partial equals is like you either tell us, or we need to do some proc macro magic to like introspect the struct and be like, oh, has it got the right derived tags on it or something like that. Like it's pretty much impossible to be able to just say like, does this struct import this trait as a without doing something at compile time to like support that.
Cool. Yeah, my last question was just on the medium. I think we've brought up and played around or discussed using the like Rust notebook tools. They're a little, the last time I played, they're a little felt a little rickety. I was curious if you had any, if you guys are using this beyond just like, do you personally use this when you are exploring stuff, or is it just for presentations?
I just did it for this meetup basically, as a way to make this a little bit more interactive.
I thought it worked really well for that. So that was a good idea.
It's incredibly impressive, and I think the way it works is kind of mind blowing. Like what it's doing under the surface is it's kind of compiling each like little code block. It's like compiling it, turning it into a dynamic library, and exposing the symbols effectively, right? So I create an OSO instance, I write rules, I OSO load string rules. Those are now like compiled into a dynamic library and given like a C interface, C binding, so that it doesn't recompile it on the next one, right? Like when I go and do query rule, it's not recompiling the whole thing to go all the way through. It's like it's linking back into the library and referencing the objects that it registered earlier, which is just kind of fantastic. Yeah, it can be awkward. I found this is my top hint here is, if you have any dependencies or imports, get them out of the way up front and try not to import stuff again, because it can often complain.
Nice. Yeah, I don't know. I thought that was great. Cool. Are there any other? Does anyone else have any questions?
Yeah, I've got a question. Bit higher level, less to do with Rust, but once you pull out the policy decisions to some other language, can you do some static analysis on that to help users try and determine if the policy they came up with is what they're actually trying to do?
Yeah, no, that's a great question. So we do I'd say like in the grand scheme of things, we do a relatively small amount of that currently. So we do have things like it's kind of like policy lints right now that will warn you if you've defined a variable but not used it, in the same way that Rust might do that. That will warn you if you try to use a type that isn't defined anywhere. The policy grammar itself is actually reasonably robust, so like stops you from writing errors just even at load time. But that error in particular is one that we're probably going to get to in the next couple of months and like invest heavily in it, because I think that's like a potentially really, really powerful error. Is what we want to get to, for example, is the ability to write tests and checks like directly against the policy to kind of assert that your logic is right, which I think in practice it's a really tough thing to unit test like authorization, for example, because it typically requires you like representing the entire policy as a test case and then writing it. It's a kind of really painful thing to keep in sync, because really it's just checking data fields against a policy. So either every time you make a change, you keep your test case up to date with that, or you just kind of don't bother. So yeah, that's like an area we want to do in the future is like a ton more work in that. So you can write like something like mocking or assertions against your policy.
So looking at your screen at line 48, so I presume that is polar right there at the end part. That's polar, correct?
Correct. Yes.
Okay.
Yes. Yeah. So this is so normally if I flick to my VS Code editor, let's see, I must have like an example. Just going to try and bring up a quick example. Okay, yeah. So here I have like a simple Python app. This will be like normally how it will look, right? So I have like a simple Python app. It's a Flask app. It has some routes to get expenses and things like that. My favorite example. Normally you'll have like a one or several Polar files. If you use something like VS Code, you'll get your nice syntax highlighting of it, and you'll represent your authorization logic in this single place. And it's treated very much like source code in your repository, right? Managed through version control, all that kind of stuff. And then maybe as part of the startup initialization, this will go through and find all the policies and load that file, for example. Then you can use that. Let me find one. Yeah, here it is. You can use things like, so this library, we wrote the authorize helper function to do like the authorization inline in a file. So I can add authorize anywhere. I can add it here inside get expense. I can maybe add it down here and get an organization, and it's all doing that, passing it in based on these objects from the app, but the logical stays here. But yeah, you can equally just load this in as a string basically, but typically you'll write it as a Polar file and load it in.
Okay, thanks.
All right.
I have another question. Are you familiar with the SLED project?
Somewhat, yes.
Just sort of tangentially related. I was reading some blog post from that guy talking about how he tests SLED, and one of the techniques is like fuzzing database operations and making sure that certain invariants are maintained. Mm-hmm. Is that anything you've experimented with or would potentially be fruitful for like fuzzing different, I don't know, policies or something?
Yeah, that probably would be super helpful. We kind of have the more traditional ones right now. We have like unit tests of the VM operations, like a single operation, does that do the right thing? And then we have a pretty healthy set of like integration tests for various different policies. But these are somewhat manual right now. We have experimented a little bit with using I can't remember exactly which one of the libraries, something like prop test or quick check or one of the, I can't remember exactly the Rust crate, but there's a Rust crate that will kind of allow you to generate the sort of combinations of inputs to a test. I think like that sort of exhaustive testing approach could be a pretty good one. Yeah, but fuzzing, yeah, some sort of fuzzing would be potentially very valuable as well.
Cool. Does anyone else have any other questions? Awesome. All right. Thanks a lot, Stan. That was really cool and really interesting. That was great.
Yeah, thanks everyone for listening and the questions.